This map shows all parts of the ocean floor that have been mapped out. And as you can see, it more shows just how much of the oceans we haven't properly studied. As for all the dark areas, there are no high-quality maps of the ocean floor available. Filling in these missing gaps is important for a bunch of different reasons, including better understanding ocean waste. But it has turned out to be an enormous challenge to do so. If you throw a piece of plastic garbage into a river or sea at a certain place in the world, is it possible to estimate where this piece will eventually end up? We can't predict anything like that, but we can make an educated guess based on data collected by buoys dropped into the sea. Our piece of plastic is first heading north to the Barents Sea in the Arctic Ocean, before it then floats through the Greenland Sea into the Atlantic. Here, something strange happens. Our piece of plastic seems to be circling in one area of the ocean, almost as if it is trapped. And it's not alone. This is the North Atlantic Garbage Patch, where much of the ocean's floating garbage is concentrated. We know this because since 1979, scientists from the US Weather and Oceanography Authority have been releasing trackable buoys into the oceans with which they can observe how ocean currents move them. Here, you can see the starting positions of the buoys, which were launched into the sea by ships and aircraft. And here, we see the migration patterns in action, with many of them drifting into the North Atlantic Garbage Patch. The data collected also coincides with computational simulations in which thousands of particles were placed across the oceans and moved based on predicted surface flows. We also see that there are other circular ocean currents, in addition to the North Atlantic, also in the South Atlantic, as well as in the Indian Ocean, the South Pacific, and the North Pacific, which has the largest one of these garbage patches. The garbage patches are the result of the 5 large ocean gyres, which are circulating ocean currents that spin waste into these specific areas. One of the issues, however, with the term garbage patch is that it evokes this idea of a thick layer that just covers part of the ocean, like some trash island. The reality is different, and it is much more complicated to get an understanding of them. Therefore, a large ocean research expedition on the Great Pacific Garbage Patch was conducted. 17 participating vessels sailed the Pacific between Hawaii and mostly North America and collected data on the amount of garbage using special nets. In addition, one boat was used to explore the main area of the garbage patch and collect information on the exact amount and composition of the waste here. Later, additional aerial imagery was taken by an airplane. Looking at the data, the scientists came to the conclusion that 99.9% of the trash found is plastic. The researchers assume that this patch alone contains 79,000 tons of floating plastic waste. They also learned more about the composition of the patch, categorizing the waste into 4 groups, from microplastics with a size under 0.5 centimeters to megaplastics with a size of over 50 centimeters. As far as the amount of weight is concerned, it turned out that the large parts also contribute by far the most. Of the 79,000 tons of plastic waste, more than half are megaplastics. And this group is mostly made up of one specific type of waste: fishing nets. While this study has contributed to a better understanding of the problem of marine pollution, it also shows the enormous efforts necessary to even just gather data in the vastness of the ocean. And this study only looked at the garbage that is floating on the surface of the water. Based on data from the North Sea and the waters of Australia, the UN Environment Programme estimated that of all the marine litter that ends up in the ocean, 15% is floating on the water's surface. Another 15% can be found washed up on the beaches and coastlines. But the remaining bulk, 70% of all marine litter ultimately ends up on the seabed. And only very little information is available about this garbage because of how inaccessible the seabed is. While we can model how floating particles move based on currents, identifying hotspots like these garbage patches, doing the same thing for the ocean floor is much more complicated. The effects that lead to floating garbage eventually starting to sink to the sea floor must be taken into account, such as degradation or biofouling, which is the accumulation of plants, algae, and microorganisms on the surface of waste. Also, further knowledge on subsurface currents, as well as the nature of the seabed, is important for modeling seafloor waste predictions. For gathering data about this issue, there are different approaches. One way is through the use of so-called bottom trawlers that collect waste. The advantage is that this way you can identify both large and small pieces and even clean up and remove them from the sea at the same time. The big disadvantage in turn is that this is an enormously invasive approach in which fish are also collected, injured, and even killed. In addition, this method is not suitable in regions where the seafloor is rocky. However, it is precisely these regions that are of particular interest, as they could be potential hotspots for garbage. Another method of collecting data is through optical mapping. For this purpose, videos or photo sequences of the seafloor are made, either by divers in shallow waters, by a camera that is attached to a rope hanging from a boat, or by underwater vehicles. These videos can then be used to create a textured 3D model of the seafloor with which garbage can be identified. This approach is less invasive, but it is heavily dependent on the optical conditions of the area, such as the clarity of water and availability of light. It also just takes a lot of time to film areas using this method. This is why there is a growing interest in a third way of gathering data about garbage on the seafloor. Sonar is a long-established technology in which the depth of the ocean can be measured from a ship. It works using echo sounders located under the boat, which emit hundreds of narrow beams in a fan-shaped array, sending out acoustic pings. This way, the depth of water can be determined based on the time it takes for the ping to bounce back from the seabed to the sounder. The advantage is that this technology allows areas to be mapped much faster than using the optical approach. The disadvantage, in turn, is a comparatively low resolution, which decreases with increasing depth. Because when the seabed is deep, the distances between the points of the transmitted beams increase. Still, using this method, scientists were able to create models of the seafloor with a resolution high enough to identify garbage laying on the ground. This sonar image, for example, taken in Italy's Venice Lagoon, shows a pile of tires on the seafloor. And here, you can see fragments of a rope made visible by the sonar depth information. There is even potential for using this method to identify and study large sinking objects such as fishing nets. And even if it will hardly be possible to map out our entire oceans in such high resolution, the collection of depth data is generally helpful. With enough data, a model of the seafloor can be created, with which computer simulations of garbage movements can be improved. But this is where the problem from the beginning comes in. For most of the world's oceans, we simply don't have that data. If you ever looked at Google Earth, you might have noticed that it does show bathymetry maps for all the world's oceans. And these maps are impressive, as you can see the elevations and depressions, the mid-ocean ridges, as well as the deepest naturally occurring places on the Earth's surface. But if you zoom in closer, you will also see stripes that seem to cut through the ocean. These lines are sections that actually have been measured using sonar technology, mainly along major shipping routes as well as by scientific expeditions. The rest of the oceans are only mapped in an extremely low resolution, using a clever but indirect method to do so. Due to the different nature of the seabed, a slightly different gravitational pull acts on the oceans. This leads to subtle variations in the height of the sea level, so that it is higher over underwater mountains and ridges than over plains and deep trenches. These differences can be measured by satellites, and that is how these global maps are made. But just how hidden the exact nature of the seafloor remains, despite these satellite measurements, becomes clear when you bring the resolution of this map into perspective. State-of-the-art commercial satellites can map areas with a resolution of up to 0.3 meters. This means that 1 pixel represents an area of 0.3 meters by 0.3 meters. And using public resources, you can find satellite imagery of all of the Earth's land surface with a spatial resolution of at least 30 meters. We've also mapped other celestial bodies in high resolution. Between 2006 and 2017, NASA's Mars Renaissance Orbiter took around 90,000 images, mapping out 99% of the surface of Mars with a spatial resolution of 6 meters per pixel. In comparison, the global seafloor maps of our oceans have a spatial resolution of just 5 kilometers per pixel. In order to create a more high-resolution map, the Seabed 2030 project was launched. Their goal is to put together all seafloor data that was collected by various organizations around the world in order to map the entire seafloor by the year 2030 and make it available to everyone. Minimum requirements have been set for the resolution, whereby deeper parts of the ocean may have a slightly lower requirement due to the fact that the spatial resolution with sonar mapping decreases with increased depth. The project is making progress, and yet to date they have only mapped 20.6% of the sea floor. As of now, their map still speaks more for what we don't know than what we do know. While the information collected here is useful for a variety of areas of research, from climate and weather forecasts, tsunami wave prediction, and even to studies on the modeling of garbage in our oceans, it is also important to be clear that a more precise understanding of the seafloor will not only be used to protect the oceans, but it can also be used for non-sustainable activities. As for example, this data is helpful for the extraction of resources in the oceans. To get a grip on the marine litter problem, it will be necessary to take a number of measures, from reducing the use of single-use plastics to implementing modern waste management around the world. And to help immediately, Team Seas was founded, the collaboration I spoke about at the beginning of this video, in which a large number of creators have come together. Which is why you may see quite a lot of videos about oceans pop up on YouTube in the near future. The goal is to raise $30 million to remove 30 million pounds of plastic and trash from the oceans, rivers, and beaches. So for every dollar donated, 1 pound of trash comes out of the water. To accomplish this, Team Seas works with 2 foundations. Half of the money will go to the Ocean Conservancy, which organizes massive beach cleanups around the world and will go out to sea for removing existing trash. The other half of the money goes to the Ocean Cleanup Project, which will take millions of pounds of trash from the rivers. With their so-called interceptors, they collect river waste so that it doesn't even make it into the ocean. For just $5, these partners guarantee that a full 5 pounds of trash will be removed. I think it's an amazing opportunity to show that the internet is more than just retweets and raising awareness, that something great can come out of this community.